Today's session we are going to discuss about simple harmonic motion. Today's session it's time to discuss about dynamics of simple harmonic motion. Remember, a simple harmonic motion is a kind of motion which is to and fro motion, or oscillatory motion, which is repetitive. So by today, when we are going to deal about dynamics refers to the motion, the study of motion, considering its cause. Its cause means force. So in dynamics, it's where we study about the motion, even the cause of motion, whereas about kinematics. In kinematics, it is a study of motion without its cause. For us, for today, we are going to consider about dynamics. Dynamics means the motion and its cause. So let's go ahead. Let's start by, if it is dynamics of SHM. So we're going to deal about the force. Remember, in the simple harmonic motion, there is a spring. This spring can have mass. Assume there is a table. On the table, we can exact a force. There is a force here, which is equal to mass times the acceleration, according to Newton. It is driving force, the force that can cause the motion. Also, for a spring, there is what we call less powering force. Less powering force, a force that always brings back, which opposes the direction of motion. So, less powering force always equals to negative kx. It means that it refers about Hooke's rule. According to Hooke's rule. Whereas according to Newton, force equals to mass times the acceleration. So remember, we have two forces. This body here is expressed by two forces, a steering force, even a driving force. So for this case, the steering force will be equal to the force which is driving force. It means that negative kx according to Hooke equals to the mass times acceleration. And remember, it means that k at this case equals to what? Remember, acceleration of simple harmonic motion always equals to negative angular frequency squared times its displacement. This is the acceleration of a simple harmonic motion. Let's plug in here. If you plug in here, negative kx will be equals to negative mass, this one times the angular frequency squared times x. So this negative will cancel out. We will cancel this one. Even then we will have k, which is equal to mass times angular frequency squared. Even this x will cancel for this one. This is what we call spring constant. So this is the result related to dynamics of simple harmonic motion. Considering dynamics of simple harmonic motion, it's where we see the spring constant. So By the next time, we shall continue by dealing about if k equals to mass times angular frequency squared. By at this time, it's possible to find the period. Now, period equals to what? Frequency equals to what? Remember, the angular frequency always equal to 2 pi times frequency, also which is equal to 2 pi over period. So, using this now, the period of superharmonic motion can be calculated, also the frequency can be calculated. So, for today, by considering the dynamic of superharmonic motion, where we consider the force, we can get the value of k as calculated here. So, let's end by here. Next time we shall discuss about the period of superharmonic motion and frequency. Thank you so much.